To review earlier, what did we create? We created a node class that's a generic class. That node class has two properties. It has a value of type t, and it has a next pointer to a next node. And we use the train analogy to say that we have a train of cars. We created our first car, which is a node of type integer, and that node has a value of 12. We also created a car which has a value of 99. We connected 12 to 99, and we were able to print it. We printed it using custom string convertible. Next, in our talking about linked list, we'll go ahead and we'll actually create a full linked list implementation using a head node and using a tail node. That defines a linked list, right? So a linked list has a head, the starting point, and it has a tail, the last car. What does that look like? So here we have a linked list. Right? We started off talking about a node, we created a node, and we used different nodes, we connected them to create a connected node list or connected linked list. But here we'll implement a linked list, and an abstract data type linked list looks like this. You have a series of nodes. Eric, can I use colors here? No numbers? No numbers? Okay, so my first node is referred to as the head, and my last node is referred to as the tail. Let's get numbers from Mr. Eric. Give us some numbers. 7, 11, 21. Okay? So here we have a series of nodes. We have a head, so the head is pointing to what value? 7. In that case, this is the first value. First. Don't keep pushing it, you say? First node. And this is the last node. Right? What is it saying? Who's that? What's happening? All right, so here we have our linked list. So we'll go one step further from a node. Because earlier with our node, we had to append using next every time, like manually do it. But we'll create a linked list class with an append function. So if I want to add to my linked list, I say append some value, right? And our linked list will also have a remove function. It's going to remove from the end of our linked list. So if I say RemoveLast, it will remove 21. Okay? Yes. We'll be making those functions. We'll be making the linked list. We'll be making a class linked list. Okay? So this is where we headed. So a node we spoke about earlier. This is our node. We started with a node. But keep in mind that most times you'll have a linked list question. It will have like a class node for you to use. Everybody with me? Because as we see, we could create a linked list of nodes. Okay? But in our example here with our linked list, we'll have a head value and we'll have a tail value. So at any point in my linked list, I could say, hey, what is the tail? Or give me the last value, or give me the first value. Right? And here, this is a singly linked list. That's a singly linked list. It's pointing in one direction. Okay? If I was pointing in two directions here, let me attempt to do this here. if I was pointing in two directions, this would be called a doubly. Right? So you have a next and you have previous. Okay? Awesome. All right, so let's go ahead and build our linked list out. We'll start off with a class. It will also be a generic class. And we'll have two properties. What's the two properties? Head and tail. Okay? And both will be data type node. So let's go create that. We can't add those properties. We can, but we want to keep it very simple, just a basic node, right? But we'll make our linked list use a node and make it more complex, okay? But yes, you can just add it up on there. All right, so let's go back some space here. So here, full implementation, not just implementation, doesn't matter. Implementation of a linked list. Okay, so we start off with a class here. We'll call it linked list. Yulia, if I want to make it a generic, what do I need to do here? Angle bracket, type T, or type Y, right? Doesn't matter. Cool. And we said we have two properties. We have a head. Head is of type node. And we have a tail, which is also of type node. And observe they're both nil here, because you could have an empty list, right? So here we do not need any initializer because they both have values. Okay? Yeah.
So is it linked to this? So when we card 12, card 9 in previous example, I wrote that it's linked to
It's a linked list, but it's just using nodes connected with the next value.
So
Here we'll be using functions. Here we'll be using functions, and it's a full linked list because it has a head and a tail property. In our node, we have no head and tail property. We created a list of nodes. Exactly, exactly. Okay, so the functions we'll be writing, we'll have a first computed property, we'll have a last computed property, we will have an append function or append method, first computed property, a last computed property, amend the constitution. And we'll have a RemoveLast method. And as the name implies, it will remove the last node from the linked list.
the last is like
The tail. Like wherever the tail is pointing, in our example here, if I go back here,
is it the first?
the last will be 21. Like if I say remove last, it removes 21.
Last and first out.
The first is 7, the second is 11, the last is 21. Yes, yes, yes. If you want to go last in, first out, yes. All right, cool. So the first is pretty trivial here. We'll have some variable. Let's mark things public here. This is a variable, and we call it first. And what do we want? We want the entire node, for example, or we just take the value. And we just return. What am I returning here? Actually, just return the entire node. If I'm saying first, what's my first? Head, right? So head is the first node. Head is the first node in the linked list. The tail is the last node in the linked list. So if that's said, if I say return last, what am I returning? Tail. For last node. And again, they're optional because maybe it's nil here. So everything happens at the end. So append method adds a node to the end of the list. RemoveLast removes from the end. Okay, the two methods we will be writing, I want us to draw them out first before we actually implement them. Okay, I'll write the stub method. So public function append, and append will take some value of type T, but that's it. We're gonna go off and draw what we want to do. And we'll come back and we'll implement it. As we implement it, if we have any errors, we'll fix it with the sketch we have. Okay? All right. So, we have a blank slate. Currently, go ahead, sorry. In our function here, this one?
Yeah, but wouldn't it be appending a
No, it takes a value. It's going to create a node. With the value, we'll create a node. The same way we created a node earlier with a value, right? It's the same thing. We'll create some new node with that value. All right, so let's go here. Okay, so we have a blank slate. We want to go ahead and implement the append method, right? So the goal is write an append function for linked list, right? So you're given some question, write an append function for a linked list. There's a few scenarios we have to go through, right? If it's empty, what are we doing, right? So scenario number one. Scenario number one, if the list is empty, what are we doing? So if we're given some number, I think Eric gave us 7. So if we have some node 7 that we want to add to our linked list, what are we doing? So we're given the number 7. We create a new node. We have a new node. At this point, we have to figure out what is head and what is tail pointing to, right, everybody? Our linked list has a head, it has a tail. That's what we're working with. So what is head pointing to in that case? Head will be pointing to 7. Do we agree? Right, so head will be pointing to 7. What's tail pointing to? Tail is also pointing to 7. Very good. So here, tail is also pointing to 7. So that's scenario number 1. Scenario number 1 says, I have a 7 node, I'm adding it to my linked list, that's the first value. So my head and my tail will be pointing to that same value, right? So far, so good. Actually, let's implement it as we go. So let's implement the first step first. Scenario number 1. So Amini was asking a question, don't we need a node? We'll create a node because we add in a new node. So let's create a node. We know how to create a node. So we'll say let new node equal to node, and the value is value. Right? Perfect. So we have a new node. We could keep going on and do scenario 1. So scenario 1, what is scenario 1? Empty list, right? So appending to an empty list. We have a new node. We want to add it to an empty list. We'll use a guard statement here. We'll say guard last node equal to, here we are guarding against the tail, because if tail is nil, that means we're empty. So here, empty list. Put a return here. So scenario 1, we use a guard statement. We guarding against the tail, because remember, we add into the end. Everybody with me? So if tail is nil, that means I have an empty list. So we'll go to scenario 1. In our scenario 1, we said new node, head will be pointing to new node, and tail will be pointing to the same node. Okay? So let's go do that in code. Okay? So here we have new node. We'll say head equal to new node. And you could even say tail equal to head in that case. We could do anything here, really. Listening? Listening? Tiffany, question? That's what I'm saying, like, it's good to draw, right? So what we drew, let's go to the drawing first and then come back. So we have a new node. So 7 is a new node, right? Let me draw this out here. So 7. That's our new node, right? Do we agree? Right? So what do we say? We say we have a new node. It's an empty list. New node, empty list. So head currently is what? Is nil, correct? Head is currently nil. Stop me. Head is currently nil. So what am I saying? I'm saying head gets set to new node. So head now is pointing to new node. Right? Tiffany? Right? We also said that tail should be pointing to the same thing. Right? Those are references. Those are all class references. They're all, if I'm pointing to, if head equal to new node, and I say tail equal to new node, they're pointing to the same thing, right? So here I say tail equal to head, right? So they're both pointing to the same object. We started with empty, but now our list has one object. We started off with an empty list, but now our list has one object. That's scenario 1. Okay? We're not going to go to scenario 2 yet unless we confirm all that works, because I don't want to jump ahead too quickly here. I'd rather come back to this than fly away. Okay, so we have our append function. We agreed that we created a new node. We agreed with scenario 1 that we append to an empty list here. In that case, if I'm in my else statement, that means I'm empty. Do we agree with that? Right? Yes? Right? Because tail is nil. Yes, sir?
We're guarding against tail.
We guarding against tail to find out if tail has a value. If it has a value, we'll go to scenario 2 later with the last node value. Right? Because later we have to change pointers.
So by default should be presented.
Yes. The first scenario, like that's what I'm saying, like the drawing part comes very important. Like you don't just add stuff without checking first, right? So first, like, is there a value? If there's a value, both head and tail pointing to the same value. If there's more values, then we have to change what tail is pointing to. And we don't want to lose tail in the scenario. That's why we have the last node there. Because we start manipulating tail, before you know it, you don't have a tail anymore. Right? Or your tail is by itself, which could happen. Right? Okay, so let's actually test this out. Remove function, right outside here, let's create a list. Create a list using our linked list of type, you know what, let's move out of let's stick with the numbers for now, that's fine. Actually, doesn't really matter. Let's do fellows. This is going to be string. And we start off with Oscar here. Actually, we don't need this, sorry. So we have fellows, and I say fellows.append Oscar. Okay. So this is scenario 1. Invalid redeclaration, of course I did. 1 second, fellows here. Just put fellows 1, fellows 1. If you have a fellows, just change the value. And then we'll stick with our fellows here. So this is testing scenario 1. Did we add Oscar successfully? We'll go ahead and we'll test it. Can I just say print my fellows? We're in the same scenario we had earlier. Here I'm trying to say print fellows, and I'm getting a compiler description of what my fellows object is. It tells me it's some swift.string object, but it doesn't show Oscar. Everybody? I want it to show Oscar. I want it to show Oscar is pointing to what? Nil. Very good. So I want it to show that Oscar is pointing to nil. That's what I want to see, right? So Oscar is currently pointing to nil. That will confirm that our append function works for the first scenario. Everybody with me? This is only for one append. We haven't done the second append. Okay. What do we need to do in order for us to have a print statement or customize our print statement? What do we need to do to our type? Custom string convertible, right? As Amini says, Chelsea, everybody right? We're on board here? Custom string convertible, so let's go ahead and do that. We'll do the same thing we did earlier. We will extend here. Extension, linked list, custom string convertible. And when you type in custom string convertible, you'll get a compiler error, because here the compiler tells you does not conform to protocol, right? There's only one value we need to go ahead and implement, and that's description. So you start typing in description, it's a variable, you press enter, and we want to return some string. We want to return some string. So we'll do what we did earlier. We will find out, so we'll guard against the tail here, else return return string. Okay, we got in against the tail. If my tail is nil, what's the state of my list? Empty. Very good. So here we have an empty list. Okay. Actually, let's start off with the head. So we want to print from the head, not the tail. If the tail is nil, the whole thing is nil anyway, it doesn't really matter, but we want to start printing from the head value. What data type is head? A node. Does a node know how to print itself? Yes. So that's magic, right? We wrote that already. So now we could, 1 second, Mel. So now we could simply say, just go ahead and print head. Mel? Oh, that's not a stored property. That's not a stored property. Let's clarify that real quickly. So if I have var name equal to 90, that is a stored property. Right? Right, everybody? So Mel was bringing up a question there. So this here is a stored property. Stored property. And you cannot have stored properties in an extension. That's what Mel was trying to clarify here. But what type is our description? Computed property. So this is a computed property. And this is a stored property, does not compile. If you see that on some quiz, does not compile. Extensions are not allowed to have stored properties. Okay? Cool. So that's good. Like we did earlier, if all went well, we should just be able to run our playgrounds again and get Oscar. Yes, Chelsea? No, we wrote it ourselves. Yeah. Right? Nothing there is given to us. We wrote everything ourselves. So back in our node, we conform to custom string convertible. That's why the node now knows how to print itself. So we could simply come here and say, go ahead and return head, string interpolation, prints the object. The object knows how to print itself because we customized it, and then we're good. Cool? It's a beautiful thing. All right, so now we could append Oscar, but if we do fellows dot append Tanya, and we print, right? It cannot do that yet, right? So we have to get to scenario 2. Everybody with me? Right? So right now we have Tanya, we appended Tanya, but Tanya does not show up because currently our function is incomplete. We only checked for scenario 1. Let's go back to the drawing board and do scenario 2. Okay, what number we currently have? Let's do fellows, right? Because we're dealing with fellows now. So let me do a change up here. So we have Oscar. Right? Awesome. So here we have Oscar. And currently we have head. And we have tail. And we have a new node we want to add. We have Tanya. Right? So we have a new node. This is a new node. Still new node. We have a new node that we want to add to our list. How do we go ahead and do that? We could talk about it. We could draw it out. Any suggestions? And remember, we add into the end. So Tanya comes after Oscar. Oscar is still the head. Forget about the code. You join this for somebody. How do you add Tanya currently? There's a dot next involved there, but what are we drawing? So arrow from Oscar to Tanya? Okay. So Tanya says arrow from Oscar to Tanya. So we'll go here. There's an arrow here. Correct? Perfect. So now Oscar.next is pointing to, we'll write it out as well. We'll say Oscar.next, for example. Or in our example there, this is last node because we have last node. Let's update this. So this is last node, right, everybody? We have this last node in our code right now. So last node, Tanya says last node dot next equal to new node. Very good. Excellent. So we have our red arrow. Are we done? What's next? What's the next line we write in here? Yes, sir.
We need the tail also.
What's the tail doing?
It must be set to the new node as well.
Very good. So now tail equal to new node. And then in our drawing, if we go here, tail will be pointing here. And this guy is gone. Right? Conceptually, this is what we're after. That's why I really want us to draw it to see what we're doing. Drawing it will make you see what you want to do next, right? So this is exactly what we have to do. We're changing pointers, right? That's what we're doing. We're changing pointers. That's what the node is doing, or the linked list rather is doing. You want to add something to the end, you got to change what the tail is pointing to. And you have to change what Oscar is also pointing to. So we did a couple steps. We did step 1 was this. Step 2 was this. Any questions? We all drawing, right? Yes? On our paper? All right. Very, very important.
The side wording, both of these notes.
Yes. All right, cool. Let's go at it. Let's go to code. Any questions of the drawing here before we go on? All right? Everybody was able to draw it and make sense of the drawing, right? Yes. What does what? Oh, one is Oscar is pointing to the new node, right? The new node is Tanya. We add in Tanya to our linked list. So Oscar is pointing to Tanya. And our tail, we need to change what tail is. Tail now is pointing to new node. Cool? All right, so where are we here? Append, append, append. Okay. So anybody could tell me what we have there written down? What are we writing here for scenario 2? So scenario 2, we drew it out. Scenario 2, we have existing nodes. What are we doing?
Last node.
Last node dot next equals to new node. And then somebody else? You go ahead. New node equal tail. Right? That's what we said. New node equal tail, where's tail? New node, not new node. Is there a new node? What's a let here? Oh, sorry. Vice versa. Write what you write down. Okay? That's all we have. So till now is pointing to new node, which is what we just added. And the last node, in that case, the last node was Oscar. Oscar's next value is the new node, which is Tanya. Okay? We should just be able to run that and see our outcome here. Go down and run. Right? Hey, look at that. So here we have Oscar pointing to Tanya. Tanya is pointing to Neil. Let's append the next fellow. Fellows.append. Append David. Right? So Oscar pointing to Tanya, pointing to David, pointing to Neil. So our append function works. Yeah, go ahead. Scroll up to the append function. Okay. Let me clear up some lines here. Questions? The 2 lines is exactly what we drew. You want us to go back through it? Okay. Anybody want us to go back to the drawing? Because that's exactly what we drew, right? We drew it and we wrote it down. And try to append, right? Make sure you append here. Try to append more fellows. Is everybody done with the append function? Yes, sir. That next comes from where? Every node has a next property. You agree that last node is a node? So now we're not manually saying that next. We just say append. Very similar to our array. Array has append, right?
When I put append, it's just bringing up like the regular append.
What fellows are you using? We had a fellow earlier.
Yeah.
So make sure that you're using the fellows to review here. We had a fellows before, which is the array. What's your fellows called?
For our fellows, I have an array of 2 fellows.
So you're referring to that array?
Yes.
No, that's a new, our linked list is called fellows, and we changed our fellows array earlier. Okay? Right, everybody? To keep it simple here, just comment this out. We were just showing that for illustration purposes. And here we could just say array implements description. Okay? Was everybody able to test the append function? Luba? Okay. All right. Great. Let us continue on. Our last function will be a remove function. So we'll start off with a public variable called RemoveLast. Doesn't take in any values, but it returns a node, optional. Just return nil for now to silence the one. Or the error. Removes the last node from the end of the list. So again, we have some scenarios here as well, some very similar scenarios to test for. But we'll first draw it out like we did before, and we'll come back and we'll implement what we drew. Yeah.
Why would you return T instead of just T?
You could just return T, but here the person has the node, so they could access the T.
Okay.
But yes, you could return just t, depending on the implementation of it. Very good. All right, so let's go back to our drawing, and this time what are we doing? We had scenario 1, write a function to append. This one here, the goal of this particular method, remove the last node from the list, from the linked list. Okay. We'll go through our first scenario, scenario 1. What's scenario 1?
If there's nothing in there.
If there's nothing in there, that's good. We'll say scenario 1, empty list. If it's empty, we just return nil, right? What scenario? I guess we'll just say return nil here. Scenario 2, what's scenario 2? If what? Existing value is? Yes. How many values you have? Doesn't matter? 1, right? So second scenario, you have 1 value. So second scenario, 1 value or 1 node. One node exists. What does that look like? That looks like Oscar. And in that case, we have head and tail. Right? So here, if head and tail are equal, that means we have 1 node. Everybody? Because right now we don't have a count function, right? So if head and tail is pointing to the same thing, that means we have only 1 node. Everybody agree? Right? So in that case here, what does that look like? This is if head equal to tail, then we have 1 node. We will save the node, so we'll say let RemoveNode equal to either of them, doesn't really matter, head or tail. So RemoveNode, and then basically we'll say head what? What's head value? Nil, very good. So we'll say head equal to nil, and tail equal to nil. Yeah. So yeah, basically if you have no value there, they shouldn't be pointing to any object. No, there's no way to really, you have to do it. You have to set them to nothing. Unless we specify it here in the logic, it won't do it. Like we have to explicitly set it to nil, right? It's like if the user clicks on the reset button on your game, you have to set score to 0, right? Yeah.
So, you see how this is, it's
Stack.
like this, right?
A stack.
It goes like that.
You have a stack here. Yeah.
Yeah.
Same. Yeah, first
Same
thing.
thing, just like, but
Exactly.
as you add new ones, it goes on
Onto the stack in that case, yes. So Tanya is using a stack example there, which is very similar to our linked list example. Also similar to an array when you're appending to an array. That's why an array, by definition, is a stack, right? Okay. So this looks good, right? So we're going through our pseudocode here. We're saying if head and tail are pointing to the same object, that means we have 1 object in our linked list. In that case, if we do have 1 object in our linked list, we capture the remove node or the node that we're looking at, and we set both head and tail to nil. Okay? And at that case, if we run the code again, it should be empty. Right? So let's actually test that out. We'll test it out. So here we say if head equal to tail, this is scenario, well, somebody said first check to see if we're empty, right? So guard, this is guard let equal to head, else return nil. This is scenario 1. 1 second. So scenario 1, empty list, right? That's what we said. No, we did not guard against tail. In that case, if head is nil, the thing is empty. If tail is nil, it's also empty.
Would it be stupid if we did like let and give a variable to head in the first one and then say if tail is equal to the variable, like to the variable we give head, instead of saying this if head is equal to tail?
We could do an empty variable. We could do an empty, like if empty. That's what you're saying?
No, I was gonna say that right now, like we're saying let head equal to like let nothing, like no name equal to head, and then the next one we're saying if head is equal to tail. So
What you're saying, I think what you're saying is here we could have an isEmpty function, right?
what I'm saying is actually very simple. If we said let head, like another word, let head equal to head, and then we said let head. Okay, never mind. It's a
No, what?
no.
No, let's write that isEmpty. It's fine. IsEmpty computed property. Let's write it. What does it look like? Public var is empty. What's my data type? Boolean, very good. And what am I returning? I'm returning head equal to nil. So if head equal to nil, it's empty. If head equal to nil, then list is empty. Right? So now we have a property that we could just use, right? To say is empty. The power functions variables, you want it, you write it, and you could use it now anywhere we want. Cool? Great. Now let's go back down here and do some refactoring for the first instance. And here we could simply say if is empty, then just return nil. What's that? Oh, go back to isEmpty? Okay, 1 second. We'll be right back here. So this is isEmpty. It just states if head equal to nil, then the list is empty. Cool, very good. And then we implement in our RemoveLast. And here we check for scenario 1 where it's an empty list. If it's empty, simply just return nil. And scenario 2 said that if head and tail are pointing to the same node, oh, nobody stopped me. We have a tangent here. What's our error say? We're dealing with custom types.
When we say if head dot value is equal to tail dot value.
Yeah, like right here on line 87, we have a tangent. We have an error. It's not conforming to Equitable. Because right now we have custom types that don't know how to they don't know how to compare each other. Right? It's not an int, it's not a string, it's a node. A node doesn't know how to compare itself against another node or how to equate itself. There's no equality there. We have to fix that. And it tells us, right? The compiler actually says does not conform to protocol Equitable. So we'll go all the way to the top. will make our node conform to equitable. So everything that's coming into our node needs to be equitable. Type T will be equitable. Our node itself will also be equitable. Our linked list will also be equitable. Everybody? Cool? So this one error takes us back to restructure our code. Any questions about equitable before we actually implement it? Yeah?
Are there any profile methods that I try to
So,
just put like I tried to just put removal on it. Are there like
oh yeah, there is a not Tiffany, sorry. Chelsea was saying, are there required methods, right? Right now, the node doesn't know what values will make it equal. So you need to go ahead and implement the static function for equitable, which we'll do together. Okay, everybody is at that error, right? Let's continue. Good? All right, so let's go up all the way to our node, and we'll make type T. So anything that's type T needs to be equitable. We'll start there. Okay? And our node class itself needs to be equitable. So type T needs to be equitable. Our node class also needs to be equitable. Because the node class itself, I need to compare a node with a node. And to compare a node with a node, that needs to be equitable. Okay? And now the compiler tells us even more errors. I need to conform to equitable here by actually implementing the required method. Yes?
By making type T equitable, we're not making nodes equitable?
No, not by default, no. Because now the node itself needs to be equitable. Type T is only defining the value, right? Not the actual node structure. Very good question, right? Type T only defines the value. It says if value needs to be like an int, a string, whatever, but the node itself needs to also say I am equitable. That way we could say if tail equal to head, right? Because tail and head, they're nodes. They're not values. All right, so we have variable, initializer. We'll put function right here. So required function for equatable. And here we'll start off with static. It's a static function. And wait for it, 2 equal signs. So here, this is a function override for equal. Function override for equal, and it returns a Boolean value. Are they equal, yes or no? Right, true or false? And what the arguments, we say left-hand side. So node versus node. So left-hand side is a node, and right-hand side is also a node. So you're comparing 2 nodes at a time. The left node versus the right node. Meaning my tail would be the left, and the right side of my equal would be head. Everybody? So this is left-hand side, and this is right-hand side. Right? Okay? So equal, this is what we're trying to do. This is the method we need to implement to go ahead and define how we'll make them equal. And now it's up to us to say what makes a node equal to a next node. We'll use a return statement. It needs to return Boolean.
And then need a space behind the equal, no?
You don't need a space there. You could put a space there, but that's, yeah. So what do I want to return? I want to say if the left-hand side dot value equal to the right-hand side dot value, and the left-hand side dot next equal to the right-hand side dot next, then the thing is equal, right? If my tail value and my head value are equal, and they're pointing to the same object, then they're equal, right? We could go a step further. We could put an identifier on our node, but this is good for now. Okay? At this point, our node completely conforms to Equitable. You'll come across, or we'll come across different methods, static methods like this, as we go deeper into data structures. There's comparable, where you have to say more than sign, right? How do you compare them? And it's up to you to say, you'll compare them if the date is smaller than some other date, or whatever it is, how are you making that comparison? But here we're dealing with equality. How are they equal? So we're providing the two values. We're saying both of those needs to be equal. Both the tail value and the head value needs to be equal. And the tail's next value and the head's next value needs to be equal, right? So this is a true-free equation. This needs to be true, and this needs to be true for the entire statement to be true, right? Back in unit 1 here, right? So just a little review. So true and true is? True and true is true, very good. True and false is false, okay? Cool. Now let's go back down to, this guy also needs to be right at our class linked list. Just make T conform to Equitable. That should be enough here, right? And moving on, so make sure your T is conforming to Equitable for your linked list, right? Because right now, whatever type T is needs to also conform to Equitable. And moving on, we have no more errors. Look at that, I'm actually looking for the error. No errors, where are we? Delete. Oh, one error, missing return. Let's just return nil for now. Okay, back to our scenario 2. Scenario 2, we said if head and tail are pointing to the same node, then we delete that node. Anybody want to walk us through what's happening here with our pseudocode? What's our first line in our drawing? Yes, Tiffany?
We said that RemoveNode equal head, so we captured the value of what it was.
Very good. So let's remove node. Excellent. Next person? Lilia? Head is nil, and we said tail is nil. Very good. And return, I don't think maybe we didn't have return here. Return RemoveNode. Perfect. So this is scenario 2. Scenario 2, if I have one node, this will be taken care of. Let's just put a print statement here. Print. Actually, that's fine. Doesn't really matter. Put a print statement in our is empty function. For now, just say empty list. What are you missing? Is your linked list? On your linked list, you have to conform to Equitable here. Yeah, because everything here forward needs to conform to Equitable. All right. All right. Let us test our remove. To make it simple here for our remove, let's just add one item. So comment out Tanya and David for now. Print it. We're not removing yet. Just print, make sure it still works here. So Oscar is only pointing to nil. Verify that Oscar is only pointing to nil before you do anything else. Because we've only done code for if it has one node. Okay? If it has one node, what do we do? So now let's go ahead and test removing.
Wait,
Yeah?
what are we returning at that point?
Test removing last node. What are we returning at that point? You mean in our remove here? We return the node that we removed.
Oh, but we're doing that in the if statement?
Yeah, right here, 102. And this guy returns a nil object, right? And this guy will also return a nil object too. Just do this, removed. Remove node is node t. So we're not doing this, and then we'll just do this. Cool? Because we still have to do more code for if there's more than one. We need to do more code there. Okay, so let's go test it out. So let's simply do fellows.removeLast. Fellows.removeLast, and let us go ahead and print fellows. Okay, and let's go ahead and run it. Right? So we should see empty list, right? Because at that point, we removed Oscar, and let's verify we actually could add again. So fellows.append luba and print fellows. What do we end up with? We end up with a luba, right? Cool? Go up to RemoveLast. Okay. RemoveLast. This guy? All right. Let me take that down a little bit here. I put a print statement inside that is empty. That's where it's coming from. Inside the is empty, right before the return. Let's take out some white spaces here. Okay. And the last one would be scenario 3. So this guy is, yes, sir.
I didn't get
You did not get what?
last time.
Luba?
Yeah.
We just appended Luba.
No, yeah, I wrote that in there.
Did you print at the end of it? After you appended, did you print? You printed? Append and print. Cool?
Wait, no,
Great.
mine is not. Can you go to,
Where am I going?
if is,
How are we doing? Can we go to scenario 3? Scenario 3, yes? Yes? Okay, off to scenario 3. Scenario 2 we did, scenario 1 we did, scenario 3. What's scenario 3? More than one. Very good. So here we have multiple nodes. Multiple nodes. Let's just have numbers for now. Actually, it doesn't really matter. We have Oscar. We have Oscar. We'll add Tanya. And we had David.
oh, this is for, wait, that one was for only if we have one?
Yep. Yeah, only one. They're pointing to the same thing. Okay, so Oscar is head, right? We join? David is tail. Okay, this is our linked list. We have a linked list, we have 3 nodes. We have 3 nodes, we want to remove David. How do we remove David? If we do this is bad territory, right? Because at this point, we lost our tail. Everybody sees that? Right? So this is no go here. This is no go. What we want to do, this is a singly linked list. If we had a doubly linked list, we could have gotten to the tail, say what's your previous, right? And previous could just say, I'm tail. Everybody with me? But if you have a singly linked list, you have to walk the entire list. You have to start from the head, which is Oscar. You have to go Oscar, Tanya, and if you're looking at the tail, you stop there, and then you do your pointer arithmetic, right? So what does that mean in our code, in our drawing? Oscar, I'll start from Oscar, right? I'll use a while loop, whatever. I'll start from Oscar. Then I'll go to Tanya, and I'm looking ahead. Is Tanya.next equal tail? That's the big breaking point here. That's where I want to stop, right? So if, in our example here, Tanya.next equal to tail, right? That means I'm here. Everybody? If Tanya.next equal to David in that case, or tail, then we want to stop and change our tail. At that point, what do we want to do? We want to say tail equal to Tanya.next. Right? So tail, in that case, would be Tanya. Actually, just 1 second. Just the what? Just the little node? Yeah, you could do a lot of things with linked list, right? You could traverse it, you could find out where you are, you could have a count on it to know where the middle is. There's a lot of different algorithm questions with linked list. Like linked list, apart from like arrays and stuff, is like one of the popular ones. Knowing how to reverse a linked list, that would be like your question for tomorrow, right? You starting to what? No, you're thinking in the right path, right? What's possible, right? A lot of things are possible with linked list there. Okay, so if Tanya.next equal tail, we need to change what tail is. Tail now points to Tanya. This is exactly what we just drew out. But Tanya is still pointing to David. Right? Does that make sense? Everybody? What is Tanya.next equal to? I mean, what is Tanya pointing to? She's still pointing to David. So we need to also stop that here. So Tanya, this should just be going to nil. Yeah. All right. Awesome. This is scenario 3. So we'll be using a while loop to actually walk through. When you hear walk through or traverse, those are the 2 big words here. So walk in. I'll put loop in through here. So loop in through a linked list. Terms, you'll hear walk in the list, and you'll also hear traverse, which is the most technical term here. Traverse means to go through. or to navigate from start to end, traverse. Did what? I wouldn't use iterate. Well, we could use iterate with the while. That's fine. You could use iterating, right? Instead of looping, I could say iterate through, right? So instead of looping here, we could say iterate. Traverse is the same as iterate, going through from start to finish. But you cannot use a for loop on our current linked list. You could use a while loop, but you cannot use a for loop because a for loop only works with collections, and our linked list right now is not a collection. It does not conform to collection or sequence. More protocols to talk about, but not today. So I'll just like put protocols here. Protocols. There's sequence, and there's collection. But the protocols we spoke about today was Equitable. We spoke about Equitable today. So protocols today. Protocols today we spoke about was, we started off with, what's the first one? Custom string convertible. So knowing what those are is good to know. Custom string convertible. And what's the other one? Equitable. And sequence collection, there's always also comparable. Right? Cool. So let's execute our last scenario, and we'll test it out as well. Okay. Awesome. So scenario 3, we need to iterate, traverse, walk the linked list. Starting from the head. So if we're starting from the head, we'll use a variable here called current node, and we'll assign it head. Okay? And we're using a while loop because we cannot use a for loop here, because again, our linked list does not conform to sequence or collection. We cannot use a for loop on it. A for loop works with a collection. It's a collection, like it conforms to collection protocol. Right now, we're not conforming to collection protocol. So you'll see while loops a lot throughout your data structures because we're creating our own custom data structure, right? By default, it doesn't have sequence and collection on it. So here we'll say while our current node dot next is not equal to nil. In other words, we wrote down tail. Why am I writing nil here? Nil would be the end of the thing. While my current node dot next is not looking at tail, keep walking. How do I walk? This is the actual keep iterating or keep traversing. And how do I traverse? I'll reset my current node to current node dot next. Very good, sir. So now, right now I don't have an infinite loop there. If you don't have that line 110, you just keep walking. Actually, you'll just keep walking until you get to the tail, but you'll get too far. Yes, one before the tail. Very good. So this gets us one before the tail. Let me write that down here. So stop at node before the tail. Perfect. So now it's just about changing pointers. And when I say pointers, I'm talking about our next pointer, just changing we have 3 pointers. We have a next pointer, we have a head pointer, and we have a tail pointer. So the pointers are abstract pointing to something. Everybody with me? When I say pointers, abstractly, I'm talking about this property, the property that's pointing to the object, right? In other languages, pointers, you'll actually see pointers, like with asterisks or whatever, right, Mr. Cameron? Right? And pointers are everywhere. Like you literally see like a pointer like this, right? Syntax like that. Objective-C too. What am I saying? Objective-C has pointers. I mean literal pointers, like syntax. You see it in the syntax. But here, when we talk about it, you ask, what's a pointer, right? But like you'll actually see syntax with a pointer. But here, a head is a pointer. It's pointing to some object. All right, so what are we doing here? So far, we have our remove node. The remove node is tail. That's what we removed. And what does tail get set to? Tail will get set to our current node. Currently, we are the one before the last. Everybody? Currently, if we get to line 115, we are looking at the node right before the tail. Everybody with me? Everybody with me? At the end of this while loop, where is my current node, actually? Where is current node? That's a question to answer. Where is current node at the end of the while loop? That's a big question to ask. Where is current node at the end of the while loop? I'm sorry? Second to last, right? Because we did not get to the last one, Luba. Because we said while current node dot next, while the current node I'm looking at, while its next value or its next node is not tail, right? So I stop the while loop before I get to the tail value, right? So at the end of my while loop, I am looking at one before the tail. Because remember, I want to remove the tail, right? So remove node, I have that, I captured that, and now I reset tail, and important there to capture the tail before. And lastly, we said that we want to do current node dot next. Remove is what we're returning, and we want to capture the thing we're removing before we reset it. On line 116, Tiffany, was that your question? Chelsea? The current node starts from the head value, right? Where we set it on 106. It starts from the head value, and the way it walks or the way it traverses is with the next pointer. We reset it here, right? It's like increment. Think about it like an increment. Well, it is an increment, right? We increment. We could basically say increment current node by 1 in that case. Yes, exactly. It's almost like saying plus plus or plus equal, right? But with the next property.
Okay, so the current node, I feel like you just said, the current node inside of the while loop.
Inside of the while loop is not the head. It starts off with the head,
Yeah.
but as we go through the while loop, it keeps walking to the next node.
And it stops at the one right before the
Yes.
This is what it equals right there.
Exactly. So it stops right there, and then outside here on this line here, we are one before the tail because we want to remove the tail. If we get to the tail, we went too far.
Can you go through this line?
Which line? What number?
16, 18, and 19.
16. What, at the bottom here? 16? Oh, this one?
So yeah, basically it's kind of
So, okay, we captured the tail because that's what before we remove the tail, we want to save the value. So let's write that in there. So save the tails node before removing the last node. It's almost like, yeah. So we save it, right? Okay, next step here, this one, on this one here. Now we take the tail pointer and we say tail is pointing to the current node, which is the one before.
The one before next.
Yeah.
Before
Before where tail was.
yeah.
So here we say set tail to node, to previous node. Set tail to node before the last node. Okay? And the last step here, we want to make Tanya, for example, or whatever we're pointing to, point to nothing. Because we removed it, we want to point to nothing. So here, set current node. Well, that sets. And then we return the remove node. Cool. Great. So let's test it out, see if it works as advertised.
But why would we not now just like assign tail to current node? Because we know of the tail.
Because it's a class reference, it will still be pointing to something unless you explicitly say point to nothing. Because even if we said current node here, like current node is still a reference, they're all class references. I need to say current node, point to nil. If I don't say that, it will still exist, right? Okay, let's go back to, so uncomment Tanya and David, put them back in. Put Tanya and David back in, and here if we print out our fellows, verify that you have Oscar, Tanya, and David. So verify you have Oscar, Tanya, and David. Remove last node here. If I remove the last node, I should get this value happening. So let's verify that by printing here. Oscar, Tanya, right? This is correct, right? Keep going. Actually, the thing works already, but we could keep going here. So print fellows, we did. Append Luba. So if I append Luba here, I should get Luba right here. Let's verify that. Print it, and we get Luba right here. Okay? Lastly, let's verify if we remove everything, will it be empty? Yes? Yes? Okay, so last step, let's go ahead and remove. So fellows, how many times we remove in here? Move all. We don't have a remove all yet, but that would be a good one. Who's gonna write that? So Siring says we'll write a remove all, right? While we code in buddies. All right, let's just see if the thing breaks. Right? We safe, right? Nothing breaks. So we're able to remove everything from the list and have empty list. Right? Perfect. We did a lot today. But we have to go to our coding buddies and do everything again from scratch. Very, 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 very important. Let's go over everything we did today. Yulia, any questions there? Okay, let's go from the top. How many lines of code we have here? Only 10. Okay. We started off by implementing a node. A node is very powerful. You'll keep hearing about nodes from here till you get to graphs. Right? It always starts with a node object. A node object has a value and pointers to things. Right? When you talk about trees, you have a node with a value, and you could have a left child and a right child, which is also a node. Right? So the node is very powerful, and understanding how to create a basic node class is important as a foundation. Right? Because in trees, in graphs, doesn't matter, you have a node there. If you're dealing with an abstract data type, you have a node. So we started off with a node. A basic node has a value and the next value pointing to the next value, and we said if we only have one pointer, in that case, we have a singly linked list, or it's only pointing in one direction. If you want to point in both directions, you have a previous node. Okay? And then we created our node and we linked it using the next pointer. That was our first part of the lesson, and that basically created a linked nodes, a linked list of nodes, which you'll see in a lot of like questions, right? They won't tell you, they won't give you a full implementation of a linked list. They'll give you a node class. Given a node class, go ahead and reverse the list. Okay? That'll be our question for tomorrow. Next up, we went ahead and we created a linked list. And the definition of a linked list, it has a head and it has a tail. Our head is a node, our tail is a node. The head is the first pointer, the tail is the last pointer pointing to that object. We wrote a first and a last, just utility variables here. We also wrote an isEmpty property here. Is the thing empty? And this is where we have our print statement that actually happens in our console here. We wrote an append function to add to the linked list. Because before that, our node, we always have to say node.next, node.next, right? We have to set it up manually. But here, if we say append, it knows how to append. It appends to the end. With our RemoveLast, as the function name says, it just removes the last one. With a node, it's important to know how to walk. With a linked list, it's important to know how to walk the linked list. Somebody might ask you a question like, hey, go through a linked list and return me the positive numbers, for example. So as you visit it using a while loop, like very similar to what we did earlier, here, you use a while, right? I keep walking until I get to whatever I want to get to. And when I get to that object, I stop, right? Any questions? We good? We have the code, it's working. So we saw a lot today. After lunch, I'll probably prescribe. After lunch, spend at least an hour or so, hour and a half to go through everything we did again today, right? With our coding buddies, go through everything we did again today, implement the node, implement the linked list, implement append, and remove, okay? Talk about it on a whiteboard or whatever it is there. And we'll give out a question to reverse a linked list tomorrow during 4 to 6. We have to write some function to reverse a linked list, okay? So if you have a reverse linked list, for example, just to give us a preview here, if I have a linked list like 7, 9, 7, 1, and for example 0, if I reverse that list, what will be the value? 0, yeah, 1, 7, right? So given 710, reverse it, okay? That's for tomorrow. But for today, basic understanding of linked lists and the node structure, right? Cool. And traversal. Traversal is important because traversal comes with the while loop here. When I talk about traversing, I'm talking about walking or going through from the head to the tail, or in our case here, before the tail. But this could easily be any search that you're looking for. Here we're looking for the node before the tail. Okay? Perfect. Okay, we'll stop here.